Hi all, and welcome back to Nanomedicine. This is Biodistribution 2 and this is Lecture 3 of Nanomedicine. So first let's talk about again the size comparisons of particles, because size is a very important parameter for the pharmacokinetics of these different particles. And so small molecules, for example, small molecule inhibitors, which most drugs are very small. They're down here. And again, we saw from last lecture, so this is a recap from lecture 2, that the smaller a particle is in general, the quicker it will be eliminated from the bloodstream and it will be able to go out of the blood vessels and hit the tissue, where larger things, which is where the nanoparticles are, will remain in the blood. So now let's move on to a more complicated model. Instead of the one compartment model that we talked about, you guys have started to look at and started to do problems with the two compartment model through your homework sets or through your worksheets that you saw in class. And the worksheets are designed to allow you to take what you know and then to push you out of your comfort zone and into starting to try to use the knowledge that you gained to start to apply it to more complex situations. And so this is exactly the one compartment model that we talked about in last class. And we've modeled this as an intravenous injection where the drug goes into the blood vessels as a bolus and then gets eliminated from the blood vessels with a rate constant Ke, and the clearance is by inactivation or excretion. So where exactly does this fail, and why does it fail? So why aren't we always modeling things with a one compartment model? Why do we have to use a two compartment model? And what is a two compartment model? So the two compartment model is necessary when the transport of the drugs in the plasma differs from that in other tissues. So as long as it's going from the blood vessels out to another compartment, and that other compartment is really important, or that's where the drug action is going to be. So in this case, how we've set this up is again in our box drawings. The first compartment is the blood vessels, and in this case we're going to say that we're going to accumulate this drug, or we want to get this drug to accumulate into a tumor. So the tumor is going to be our second compartment. So again, we're going to make some assumptions. We're going to assume that there is no drug in compartment 2 at T = 0, that the chemical reactions are negligible, so we're not accounting for any kind of binding or anything, and that again the drug distribution is instantaneous. The boundary conditions for these equations is the concentration in compartment 1 equals C0 at T = 0, so you'll recognize that from our one compartment model. And then also that the concentration of the second compartment, in this case the tumor, is 0 at T = 0. So the central compartment, or C1, is the drug distributed in the plasma, and the peripheral compartment is C2, is the drug distributed in an organ or a group of organs or a tumor or some other place where the drug needs to get. And so in this case, we've again done an IV injection into the blood vessels. There is an elimination here with a rate constant K1, but now here we've picked up two different constants, K12, which is the rate of which the concentration of the drug is going from the blood vessels into the second compartment, and in this case it's the tumor. But of course anything that goes in can also go back into the vessels from the tumor, and so that's a constant K21. Those two drugs, or those two rate constants, mean that the drug is staying in the system. However, the elimination constants K1 and K2 are removing the drug from the system. There's another term that we have to introduce into this, and that's a volume term. And so the volume between the two compartments, although I've drawn them to the same size, they can in effect be much, much different. And so in this particular example, the volume of the blood is 4.1 liters, whereas the typical volume of the tumor is much smaller. It's about 100 millimeters cubed. So you have to take into account the differences in the volume, and that's because we're looking at concentrations. So the amount of drug that goes in when the volume is smaller or volume is different, the concentration either goes up or down. So now I'm going to introduce you again to the idea of the mass balance equations. For this, we can write equations that will represent the two-compartment model. So the volume 1, so again, we have to introduce this volume term. So the volume in the first compartment with dC1 over dt equals the volume of the second compartment, the amount of drug being taken away from the second compartment, so that's K21, and then the concentration in that compartment at a certain time, minus volume 1, K12, so what's leaving that compartment, and the concentration that started there, minus volume 1 and the elimination constant and the concentration that started 1. So this is, again, the first compartment equation. So this is the concentration of compartment 1 over time. So again, it's the second compartment, K21, so what's coming from the tumor going back into C1, minus what's leaving that compartment, which is denoted by here, K12 here, minus what's being eliminated through this rate equation, through this elimination equation. And in a similar fashion, we can go ahead and we can model the second compartment. So the second compartment concentration over time equals the volume of compartment 1, K12, C1, minus the volume of compartment 2, K21, so what's leaving it, C2, so again, this is the term for what's leaving the second compartment, minus volume 2, the elimination constant, C2. So this is what's being added from the first compartment, so it's flowing from the IV into the first compartment, into the second, so this is what's coming into that second compartment, minus what's leaving it through going back out into the second compartment or just being eliminated from the system. And this, when we graph it, is a bi-exponential decay. So what's happening to the concentration of the drug over time when in the first compartment is you get a bi-exponential decay. So again, this is a delta function just like in the first compartment model, and it's an intravenous injection. So that means that everything is injected and homogeneously distributed all at once. And so that's your y-axis. Here's your concentration. And it is decreasing from that first compartment, which is your blood vessels or your plasma, at a rate, and then it ends up being a bi-exponential decay because this is a two-compartment model. On the other hand, the tissue compartment, or in this case the tumor, at t equals 0, there's nothing in there. It's all in the blood vessels. But over time, the drug is going into the blood vessels and it accumulates until it hits a maxima or the plateau. And then this is where no more drug is being put into the plasma, and so the decay constants or the elimination constants are actually now going to overwhelm the equations, and you will get an overall decrease in the tumor or the tissue over time. So just like in the second or in the first compartment model, we can go ahead and model the blood half-lives of this, except for this is by exponential decay, and so there are two equations. So T1 half lambda 1 equals 0.693 over lambda 1, and T1 half of that second component equals 0.693 over lambda 2. So there's a lot to put these down, or to simplify these into these two equations. We actually took the mass balance equation from up above, added in all of the concentrations, and then did the ordinary differential equations to solve the half-lives of the two different parts of the bioexponential decay. If you're really excited about that, I'm more than happy to walk you through the derivations. If you're not, then these are the simplified versions of these equations. And again, just like in the one compartment model, we can also model body clearance. So CLB equals volume 1 KE C1 over C1 equals volume 1 KE, which equals volume 1 lambda 1 over lambda 1 times lambda 2 over 1 minus alpha lambda 1 plus alpha lambda 2. So again, you'll recognize that as an ordinary differential equation. I've just gone ahead and solved it for you and made it a lot easier. The area under the curve, which again is synonymous with the exposure of the compartment. So area under the curve of the first compartment equals C0, so the initial concentration, alpha over lambda 1 plus 1 minus alpha over lambda 2. And the area under the curve of the second compartment equals C0 alpha 1 minus alpha times lambda 2 minus lambda 1 squared over, here is the a term again we introduced to solve the equation. It's just a constant, 2, 1, lambda 2, 1 minus alpha lambda 1 plus alpha lambda 2. So again, if you're very interested in how we derive this, or this would help you to understand it better, please see me, and I'm more than happy to walk you through the derivations. I will also put slides up on Colab that again walks you through these derivations. These cases are not as simple as the one compartment model, and so it's not as easy to relate these things biologically. So I'm going to go ahead and give you an example of molecular weight 150,000 versus molecular weight 50,000. And then in the next slide, I'm going to give you some homework where you can play with a simulator on the web, and so you can get a feel for what happens as you change the different parameters. But for this slide, when we're looking at an antibody that has a molecular weight, for example, of 150,000, the alpha constant becomes 0.27, and lambda 1 will be 1.9 times 10 to the minus 4 10 to the minus 4 over second, and lambda 2 is 7.4 times 10 to the minus 6 over second. Whereas something that's much smaller, which is a Fab, it's a fragment of an antibody, it only weighs 50,000. The alpha constant is 0.68. Lambda 1 is 2.4, so the lambda 1 is much quicker, and the lambda 2 ends up being much quicker. So this is just exactly in keeping with the one compartment model, where size again is a very important parameter of how long it remains, or how long something remains in the blood. There are other parameters that will change that general rule, but again, in general, size is a very important predictor of pharmacokinetics and how long something remains in the bloodstream. So here's your homework, the two-compartment model. It's an online simulator, so if you go to this website, just copy and paste into this website. Spend about 20 to 30 minutes on this, and so you would have been doing this in class, so spend 20 to 30 minutes on this, changing the different parameters, and here is the work that's due for next class. what happens when the amount of drug injected is increased. And so this should be all of these should be answered in a paragraph describing what happens when you change each of these different parameters. So go ahead and pause the lecture and spend about 30 minutes completing this work. And that is the end of this lecture, the third lecture in the nanomedicine course series. And next time we will be talking about making things a little bit more complicated. Up till now we've been talking just about intravenous drug injection, but like I mentioned in the second class, there are more than one routes of administration, and so we will talk about the advantages and disadvantages in each of those routes of administration. And we will also introduce an absorption component of this, because not everything that will be ingested or injected will actually end up into the bloodstream, and so we will have to correct for that. So see you next time.